Before I get into the conversation that we're going to have here today, I'm going to take a little bit of time to have a conversation with you about the way that we're going to have this conversation. So working at a university for the last 6 years has made me a little weary of these big academic style lectures where someone stands in the front of the room and just flaps their gums at you for an hour, mostly because I don't really like to talk for that long, but also as a pedagogical tool, it's not particularly useful. Even if I were to be wearing, I don't know, say an American flag catsuit up here on the front of the stage, there'd be maybe 20 minutes I would hold your attention, at which point you would start checking Facebook, no matter how much you really did care about what it was I was talking about. So as a result of this, the first part of the talk, it is going to be lots of me sort of talking at you, but the second half of the talk is going to be interpretive dance. That's just a joke, no. The second half of the talk is going to be live coded. So if you want to participate with the coding section, which I really, really encourage you to do, you can get the data for the talk here, so just clone this repo, and that's supposed to be an under, but it's rendered a little strange in the fixed width font here. And we're going to be using these Python libraries and these outside libraries that you see listed on the slide. So if you want to, now would be a good time to start installing some of those if you don't have them already. So SQLite should already come with Python. If you have Python installed, you all have Python installed? And you might feel like MongoDB is kind of a big installation to run on the laptop that you have with you, and maybe you don't want to do that, and that's totally fine. You'll miss like 1/2 of one example, and they don't build on each other, so you won't be out of it for the rest of the talk. Now, the reason that we're doing it this way is sort of twofold. So one reason is for these educational reasons, and the other is more sort of an emotional one. So one of the reasons that I really encourage people to live code during their talks is that if you want to try the examples along with me, you have time to, and I really do encourage you to. So if there is some sort of a fundamental thing that you don't necessarily understand during this talk, if you're just listening to me say words about it, it might not occur to you that you're not 100% on board. But if you try to type out the code to achieve that in your computer and it throws an exception, that's your computer telling you that maybe you're missing something, and this would be a good time to ask a question. Or if you're coding along really nice and happily along with me and blah, 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 and you write the code and it runs just fine, but you have no idea what you are doing, this would be a great time to raise your hand or to be like, hey, Dillon. I'm Dillon, by the way. Hey, Dillon. Or to throw something at me and ask a question, be like, hey, we wrote this code and I don't really understand what it does. And that way, we can all learn about what's going on behind the scenes, because if you're confused, someone else probably is too. Please don't actually throw anything at me, though. Now, the second reason for this, that I encourage people to do this sort of live coding, is for the emotional benefit of it. So I give myself probably even odds within 10 minutes of live coding in front of an audience of making a stupid syntax error, like forgetting to close a bracket. Now, if you're someone who is new to Python, watching people that are the experts in the front of the room giving the talk make the same types of stupid errors that you do can sort of bring down this feeling of anxiety, this feeling of like you are an imposter here and these people that are wizard coders. So if all you ever see as a new learner is all of your failures and all you see of everyone else's work is their successes, it can be very, very discouraging and can end up as sort of a non-starter. Now, the other thing that happens is if you see me make a code mistake up here on the stage, you can watch me go through the steps of figuring out what it was that went wrong and how I fix it. So that if you are a new learner, you can emulate this behavior when you see your own code mistakes and not just get frustrated and flip tables and throw your laptop. So if we are a community that really cares about being open and welcoming to people that are not necessarily super computer savvy, I think this is something that I would encourage all of you to do. That was a really long preface. So until very recently, like 2 days ago, I worked for a place called the DLab. So this is a mixed research and services unit within the University of California, whose mission is to help researchers apply advances in technology, especially computational technology, to their research. So if you are someone who is a scientist, you can come to us and we will help you use these advances in technology all the way from how you write your research grants to how you do your final reporting on your project. Now, if you are someone who does this kind of research, I would encourage you to pay us a visit. If you are a corporate sponsor who is super interested in giving us money to help scientists become more technologically proficient, you should also pay us a visit. I keep saying us, even though I guess I'm not really there anymore. This is the web address. This is the Twitter handle. I would highly encourage you to check us out. Now, while we at the DLab have had corporate partnerships in the past, since we are within a university, most of the user cases that we see, most of the workflows, are not this sort of, I am a company that has infinite resources and I need to slog through petabytes of click record data every day. The use cases that we see are, I'm someone who has a laptop and maybe enough grant money for a software license, and I have a few gigabytes of data that I need to work through in a way that doesn't make me crazy and doesn't hog my laptop for the entire day. And so it's that particular use case that we're going to be talking about here today, although the DLab as a whole does the whole gamut. So everywhere from single case studies of like journal logs of a person to New York Stock Exchange financial record data. Now, if you are someone who is working with data that is large, so here we're meaning gigabytes of data, enough that it might questionably fit in your memory, but definitely fits on your hard drive, there are a couple of distinct but related issues that you're going to run into while you are working. Now, the first of these has to do with memory overflow errors. So it could be the case that even if your data is only a few gigabytes, maybe 2 or 3 gigabytes, when you get it into memory and you start performing computations on it, the actual amount of memory Python uses can grow very far beyond that. And if you're working on an 8 gigabyte laptop, you might eventually run out of space, especially if you have Chrome open, because that is hogging 5 gigabytes of your RAM already. Now, this is not usually such a problem with structured data, but if you're someone who, as part of your processing pipeline, ends up dealing with a lot of unstructured data, so text data, maybe you are someone who is ingesting political blogs and you're looking for similarity metrics, trying to cluster blogs by the way that they talk about politics, for example, and you decide you're going to roll your own solution to building document vectors out of each of these text strings that can easily balloon up in Python using just the base Python objects into 4 times the size that it occupies on disk. So this is a very real concern. Of course, there is the even more simple concern of, oh, my laptop has 8 gigabytes of RAM, and I have a data file that's 10 gigabytes, I can't even load it into memory to start performing operations on it, and how do I work around that? Another very vexing problem is when you're dealing with large amounts of data, it can take a lot of time to process. Now, this can manifest itself in a couple of different ways that it might impact the workflow that you have. So in one of these situations, maybe what you're trying to do is some sort of exploratory analysis of the data that you have. And every time you load up your code, you pull the data in, you run the metrics, then you have to sit around and wait for everything to compute. And if it takes more than just like a few seconds, if it's taking minutes, like 5 minutes or 7 minutes, now you're sitting there and you or the user are idle. Your computer is busy, but you're twiddling your thumbs. And that is not enough of amount of time that you can really switch to another task and get your head into it and do useful work. And then switch back to looking at the code you have just run and how you might want to modify it to look at something in your data that's a little bit different. So this can be very, very frustrating. It can make it very hard to see the actual structure that underlies your data because you're going to keep getting distracted from what's going on. One of the things we know from teaching people about how computers work is that interpreted languages are easier to learn than compiled languages because of the speed of that read, evaluate, print loop. When you can interact in real time with your programming language, you are much faster at understanding how it works. The other issue here is if you have some sort of deadline that you have to meet. There is some constraint on your time. So maybe you get data in the morning and you are processing a whole bunch of it and you have to turn it around to someone else to generate a report in the afternoon. If you only have 4 hours to run your analysis on this data, you have a really hard limit. And if it starts taking 5 hours, you need a way to speed things up. And finally, if we start thinking about the solutions that we might apply to these 2 problems, the process of thinking up a solution generates a problem of its own, which is how do we keep code complexity to a minimum? So it's often the case, and because things like Hadoop and Spark are very popular now, if you're dealing with gigabytes of data, for people to recommend that you get a cluster and you throw your data out to it. But if what you're trying to do is process 10, 20 gigabyte data file, provisioning a Hadoop cluster, sending your data over, rewriting your entire analysis pipeline to run in Hadoop instead of your native Python and getting the results back is going to take longer and probably cost more than doing it just in-house on whatever single node that you already have. And it's also going to put you in a situation where even if it were faster to process it, and even if it were cheaper in the long run, you are still going to be having to learn how to provision a whole EC2 cluster instead of just working on your laptop. You're going to have to learn how to configure Hadoop to run correctly. And of course, then you have to worry about your code maintainability if it's a whole bunch of stuff that's in Java that maybe you kind of understand because you picked it up, but no one else in your organization does. So we want solutions for memory complexity, we want solutions for time complexity, and we want to create those without code complexity. So simple on your laptop, but still effective. One solution to dealing with large amounts of memory being used by your processes is to process it sequentially in little bits. So this is commonly referred to as chunking. So if you have some sort of rectangular data frame with a gazillion rows, you can read in maybe 1 million at a time, do some processing on them, write it back out to disk, and move on to the next one. In terms of time processing, we also have a set of options here, most of them involving something like parallelism. So you can think about the different tasks you perform during your data processing pipeline as being optimizable in a number of ways. So you can optimize them at the very, very low level in terms of these subroutines you're calling on individual bits of your data. So if, for example, at some part in your process you have vectors or matrices that you're multiplying, doing this in base Python is going to be a lot slower than using an optimized library for doing this for whatever particular hardware that you have. If we go sort of a step above that in layers of abstraction, you can think about this whole process of your data. And maybe it'd be possible to split those up into parallel chunks and process those each in parallel across the different cores of your machine. So it's not a specific thing anymore, like adding two matrices together, but the whole data flow where you're reading data in, processing it, and writing it back out to disk. You can take that single process and split it into multiple processes that run concurrently. And finally, you can think about parallelizing over the range of tasks that you're trying to perform. So if you have a bunch of parallel tasks, and especially if they don't need to talk to each other at all, so you have 1,000 log files that you need to perform some analysis on and write those results back out to disk somewhere, there's no need to run those sequentially. So you can optimize at this level as well. Now, at this point, I'm going to move into a Jupyter notebook, and we're going to code up some examples together of how to do this. All right, so now I'm in a notebook. So I've opened a notebook in Python 3. And the first thing we're going to talk about is those ways to manage the amount of space things take in your computer's RAM. So the first strategy that we're going to talk about is one that allows you to sort of see what's going on at a very high level. But it's not going to be super efficient. It's sort of just to give you an intuition about what's going on. And as we go through the examples, we'll see more sort of lower level and lower level examples of how you can manage this. So the first thing that we're going to do is we're just going to read in a data file line by line and build an accumulator ourselves for generating chunks that we then pass out of a function. So on your hard drive, if you downloaded this repository, there's a little data file called data.csv, and that's what we're going to be working with for most of the class today. So again, the goal here is to build an intuition about what chunking is doing. And in our first code block, in case you haven't seen this before, we're just going to build an open constructor, so a file for data.csv. And we'll be good as citizens and specify that it's in read mode. And then we can say for line in F, I want to print that line. And what you'll see here is just the output of the different lines that are in this data frame. Now we're going to make this a little more complicated, but only slightly. So we're going to define a function that's going to pull those lines off of disk and is going to build them into an accumulator that we control ourselves. So we'll call this something like read chunks. And read chunks is going to take just the file path, and maybe we'll also allow it to specify a chunk size. And what we're going to do here is very similar to what we did above. We're going to open that file path in a read mode. And then we're going to initialize a mutable container that can catch the results of what we're doing. And then we're going to go back to that for line in F. If the length of that result that we're collecting these lines into is equal to that chunk size that we set above, we are going to yield that result. And then reinitialize that empty result. And then finally down here, append to that result, whether it's empty or it has a thing in it, the output of a helper function that we'll write in just a second that we'll call convert line. And then finally, when we run out of things to read out of this file, we're going to yield that result. Now, the next thing that we're going to do is just write that little helper function that we were talking about. So we want to define a function called something like convert line. And it's going to take a line, and basically what we want to do is just write, it's kind of a gnarly list comprehension that will take this and just turn it into an array for us. So what we want to return back is an array of floats. So list comprehension to generate an array of floats. So a float of an item for each item in line.split, and we're splitting here on the comma, so this is a comma delimited file. The one way up here? Sure. Yeah. Now, there's one more thing that we need to add here, and that's just a little thing to handle. I'm sorry? Yes, there should be. It's for item in line.split. Thank you so much. For item in line.split. And again, splitting on that comma because it's comma delimited. And one of the things that's going to happen, if we run this on the file as is, it's going to spit out carriage returns at us. So we just want to make sure that we are controlling for the case where we get those Unix new lines. right, I'm feeling pretty okay about this. We're going to go ahead and run that cell, and then we're going to come down here. And because we don't want to print out the whole contents of that file because there's a whole bunch of lines in it, we'll just set some counter here at the start to 0. And then we'll say for chunk in read chunks, where that file path again is data.csv. And I need to specify the chunk size, which, I don't know, we'll make it 10. And then we'll say if I is less than 2, so we'll just grab the first 2 results, print chunk. And then we're going to increment I by 1. So I'm not saying that I was expecting a round of applause, but like we just wrote some cool code. So some smiles would be great at this moment. Yeah. So this is essentially just what a chunker is, right? So it's pulling data off disk, and in this case, it's in a particularly dumb way. And it's patching it into a chunk that is going to give you one piece at a time. Now, you might think, surely someone has already done this. Maybe you're channeling your inner Raymond Hettinger. There's got to be a better way. And it turns out, if you're someone who uses Pandas, that there is built-in support for reading in chunks in Pandas already. So I'll make another quick note down here. We'll just call you chunking in Pandas. So the first thing that we're going to do is import Pandas as PD, just because this is the convention. And on the next line, we're going to use Pandas' built-in method for reading in data frames from comma-delimited files. So this is pd.read_CSV. And again, we're going to give it the path to that file. Pandas does not have intuition about whether or not to assume there's a header, so we have to specify here that there is none. So we set header equal to none. And if you've read in data from disk in Pandas before, this looks exactly like everything you've ever done, and it returns a data frame. If we include one more keyword argument, and that is this chunk size equals something. Instead of returning a data frame now, it's going to return to you a generator. So because I read Steve McConnell and I believe in variable names, we'll call this generator. We'll say generator equals pd read_CSV, and we're giving it that file path data.csv, that the header is not there, that we want to read it in chunks of size 10. And what's nifty about this one is this generator is actually going to yield to you like mini data frames that act just like other data frames in Pandas. So we're going to do a similar thing that we did before. We're going to set I equal to 0, and then just say for chunk in generator, if I is less than 2, we're going to print chunk. And then down here, make sure that we increment I so we don't get stuck in an endless loop forever. So what's happening here is exactly what we did. Not exactly, but pretty close, to what we were doing above, where we were just reading in data line by line. And then putting it in a chunk and returning that chunk to the user. So this is, Wes McKinney is now doing it for you, and he's smarter than me, and so this is going to be better than my implementation by more than a little bit. So you can run this cell, and what we see here is that we're going to get 2 distinct data frames out of that chunk. And we've sort of been ignoring like the whole data processy side of this, but of course at any point in this process, you can change what it is you're doing with this data. So we're just returning the data as is, but instead of just printing the chunk, you could print like the max for each of the columns of the chunk. And we're going to run this again, and in this case, it's the columns are displayed on the left for whatever reason. And you see these are the maximum values for each of those columns of data. And this is like a very small file. It's a toy example, but you can imagine if you're dealing with an enormous amount of data, you might just want to grab some maximum values for things as you iterate through the entire extent of a data frame, but not have it all in memory at the same time. So this is pretty cool, but it's still not super efficient in terms of the way that we're moving data from disk to memory before we're performing any kind of operations on it. So if you want to be slightly smarter about this process, you can change from saving your data on disk as a text file to saving data on disk as a different kind of file format. So the first thing that we're going to be talking about is something called the hierarchical data format. And the current version of that data standard is 5. So it's called HDF5. And there's a library for this in Python called h5py. So we're going to go ahead and import h5py. So HDF is a data structure. It's a binary data format that in a lot of ways mimics the sort of branching tree structure of the file system on your computer. So if you're used to navigating your file system, this is going to work exactly the same way, except that instead of changing directories up and down, you'll just be passing keys up and down. And I'll add that there is a bug in h5py where after you open a file, like even if you close the file, it doesn't actually close until you kill your Python kernel. So try not to make a mistake during this part of the talk, because you'll have to restart your notebook. So what we're going to do here is open an HDF5 file that contains it's the same data that you've been working with, but just in this different format, and that's already in the repo that you've downloaded. So instead of using the width structure this time, because we don't want to necessarily do this in a loop, because h5py will give us weird errors, we're just going to declare f is this file object that in, yes, h5py, you create from the class called file. And in this case, we're going to give you the name of the actual hierarchical data structure that could theoretically contain anything, but right now it just contains our data. And this is going to be called demo.hdf5. And in this case, because we might want to play around with it a little, and we're also going to specify that instead of just reading this in, we want to be able to write to it if we want. Now, the way that you're going to see what's in the top level of this particular data structure is just by using the keys command. But because h5py is a little strange, it returns that as a generator, not as an actual object that you can inspect. So we're going to have to do the trick where we wrap it in list. So I'm going to call list of f.keys. And this will open the file and show you the only object that I put into that hierarchical data structure, which is data. The same data that you've been looking at. Now, what's nifty about HDF5 is you can pull particular parts of that data off of disk, just like you were slicing something that was in memory already. So I have this file object f, and I can get my data out of it by passing it the keyword data. And then I can say that I want, I don't know, the first 3 rows. So just the same way that you would slice through a NumPy array, you can slice through these objects on disk. And hooray, there's the data that I've been used to looking at. Now, what's even more cool about HDF5 is that in this particular case, we have stored this data on disk pre-chunked. And because HDF5 knows where each of the bits of the data are, if I'm only reading data from one particular chunk, it's not going to bother pulling those other chunks off of disk into memory. So we can be really smart about our memory usage this way. This is particularly handy if, for example, you only want particular columns. So we're going to say just f.data just to prove to you that I'm not lying. Ooh, or maybe I am. There we go. That our particular chunk size here is, and this is actually the entire size of the data frame. But we can do something a little different with that. So what we can try is we'll say we want to make a new data set in here. And the way that we do that in H5Py is through a method call called createDataset. And because we're tracking objects through this hierarchical format, the first thing we need to do is give it a key that we can use to find it later. And we'll call you test because I am not feeling super imaginative at the moment. Now next, you can either give it the size of the data that you expect to put in it, or you can actually pass it a data object. So we're just going to give it some data, and the data that we'll give it is, I don't know, a range of 10,000 integers. Now if we create it like this, this will go in one location on disk, like one contiguous spot, and it'll be read in that way too. But what we can also do is say that we want to read this, we want to write this out to disks as chunks by specifying a chunk size. In this particular case, this is going to be a tuple. But we're only going to give it one number since we only have one dimension. And in case you haven't seen this, the comma is just there so that Python knows it's a tuple and not just parens. All right, we're going to run this. We have our new data set on disk, which is just a whole bunch of integers. And what I can do now is I can pull that data set back out by that key name. And look at the chunks attribute, and this gives me the chunk size that I set. All right, now we're going to be good citizens, and we're going to close that file, even though it's still going to be open until you quit. But this is good coding practice. Now, the last bit of memory management that we're going to talk about today is about using systems that are actually designed to intelligently monitor their memory usage and shuffle data from memory to your disk drive in ways based on how it anticipates what you're going to be looking for next. For those of you that doesn't sound super familiar, what we're talking about here is databases. So if you've only ever stored your data on disk and you haven't used a database, you should give it a try. It might feel pretty okay. And we're going to go through two examples, two mini examples. These are like bite-sized examples. I would call them vignettes, but that sounds like a little snooty. And the first one that we're going to do is we're going to use SQLite 3. Not because this is the best SQL database or necessarily the one that you should really be using for most things, but the syntax between SQL API and Python are like the syntax is usually pretty similar. So this should translate pretty well from one to the next. This was originally, I had this worked up in SQL Alchemy, but you have to import like 10 things to read in the right ORM, and it's more of a nightmare than it's worth for just this little demonstration purpose. So what we're going to do is establish a connection to the database that we have on disk. And this is, again, in that repository. So that connection is going to be SQLite3.connect, and we just give it the file name, which is demo.db. And then if we want to run queries, we have to create some sort of cursor object, and traditionally this is designated with just the letter C. All right, and we're ready to roll. So the first thing that we're going to do is give the database a query command to look at. So in this case, we're just going to select all the things that are in this particular table. And we'll do a similar thing to what we did before, where we start off by making some incrementer and using that to limit the number of results that we get back. And we'll start by creating a loop where we say for row. In that C stands for the cursor, which already has that query loaded into it. So using that query, we want to fetch many. And we're going to pass it an argument to let it know how many we want back. And this is not how many records we want back, so we'd specify that with limit, but how many records it should fetch at a time. And we'll make that 10 just for the purpose of conceptual similarity. And then we'll say if I is less than 3, we want to print that row. And then we want to increment that counter just by 1. Now, the database here isn't going to return a chunk to us. It is going to return just these individual rows. Because what we've done here is we're sort of pushing the chunking responsibilities and the memory management responsibilities away from us to this database that was written by an entire group of people who spend all their day thinking about this so that people like us don't have to. And when we run this just as we expect, and we get these nice rows at the bottom with a very minimal memory footprint here. So we could also do a similar exercise with a NoSQL database, so something like MariaDB or Mongo, but it looks like most of you are already beaten into submission pretty hard, and there's a whole part of this talk that we haven't gotten to yet, which is about parallelism across your tasks. So we're going to go ahead and move to that, and if you're like super, super angry that we didn't talk about Mongo, you can come meet me later, and we'll work through it together. So we have just been going back from, or spending this time talking about how to manage memory very explicitly ourselves versus sort of pushing it down to the lower levels of what's happening in our computers. And we're going to go in sort of the reverse direction for thinking about parallelism. So we're going to start at this very low level where we're allowing NumPy in this case to do most of the work for us. And then we're going to sort of go up to managing that parallelization process ourselves. So the first thing that we're going to talk about for this parallelism part is parallelism inside of routines. I think I might have called this a subprocess above, but the idea is essentially the same here. So we're going to start by importing NumPy as NP, as is tradition. And in this particular case, I'm going to cheat a little bit and let NumPy read an array from pandas reading in the file from disk, because I don't want to have to parse the CSV myself. So we'll read in a data file for us to play with, and we'll just call it data. And that data is going to be a NumPy array forced conversion of a pandas data frame returned by PD read underscore CSV. And that data, again, is just called data.csv. And again, we have to specify that the header here is non-existent. And then just for fun, now that we have this whole thing in memory, we can look at the shape attribute, and we see that we have an array here with 100 rows and 10 columns. Now, behind the scenes, a lot of the very simple tasks that you might ordinarily do in base Python have been overloaded by special NumPy operators that call like a whole bunch of crazy secret stuff behind the scenes to make your code run wickedly, wickedly fast. So in this particular case, we're going to play with just a little bit of matrix algebra to show you just how fast NumPy's, it's not really a NumPy implementation. So what NumPy is doing behind the scenes is it's calling specific linear algebra libraries that exist on your computer already, like BLAS or LAPACK, that are configured to be optimized like specifically for your CPU and like memory cache sizes around your CPU. So super personalized, super quick. But to show you how quick it is, the first thing we're going to do is write like a really bad matrix adding function, just for comparison. So we'll call you like, I don't know, dumb add. And dumb add is going to take two objects. I'm going to call you x and y. And this is going to be just an atrocious implementation. Don't ever do this in practice. What we're going to do is iterate through the row indices and the column indices, and then just add the values from one of those matrices to the other one. I'm going to return the original. So in this case, we're going to add all the stuff that's in y to x, and then just return x to the user. So we're going to say for the row index in, not the length, in the range generated from the length of x. And we're making like a whole bunch of really nasty assumptions that they're the same size without checking. This is not defensive programming. This is like offensive programming. And after we've gotten the row index, we're also going to want to iterate through the column indices. So we'll say for column index in the range of the length, and we'll just pull out the first row from x. So we're going to iterate through the indices of the rows, and then iterate through the indices of the columns to make sure we cover the whole space of the matrix. And then we're going to set the value of x at the row index and the column index to be incremented by the value of y at the row index and the column index. And then finally, we're just going to return x. All right, so we have our function. And what we're going to do is use a little bit of Jupyter magic called time it to see how long it takes this particular code to run. So we'll call dumb add on that data frame I have, sorry, the data array that I have, again with that data array that I have. So this is going to run it through a couple iterations to see how long it takes. And it's giving us the best of 3 tasks, which for a data frame of this size was 800 something microseconds. So that seems pretty fast, but if we take this data array, which is already a NumPy array, and we call time it on NumPy's overloading of that addition operator, our best of 3 loops hits about 1 microsecond, which is a little bit faster than 800 microseconds. And it says there might be some caching going on here, but like even if it did take, what is that, 27 microseconds, that's still an order of magnitude faster than the implementation that we wrote ourselves. So if you're doing a lot of functions where it's math heavy, lots of adding, lots of matrices, lots of vectors, you should be using these parallelized implementations written by people to call in these blasted lane pack libraries. Because if there's a lot of this, it will speed your code up quite a lot. All right. So that's how to parallelize stuff within a routine, which is basically let someone else who is a physicist do this for you. The next thing that we're going to talk about is the parallelization within a process. And so this is actually pretty nifty. This is a newer thing. What we're going to be using is a library called Dask. So Dask is a set of tools that mimic data structures that are created by NumPy and Pandas, and I think also lists is one of them. It allows you to perform what are called graph-optimized operations. So when you build your analysis pipeline, it's not actually going to compute any of the data. And what it's going to do is add tasks to a graph. And then when you run it, it'll find the quickest optimization of how to delineate your processors between each of these tasks, and then it will run the job for you. If you've used Airflow, I think there's a talk on it later today, that uses sort of a similar system, but for a much, much different reason. And if you want to look this up later, these are called Directed Acyclic Graph Networks, usually abbreviated DAG. So from this library Dask, we're going to import data frame, which is Dask's mimic of Pandas data frame objects. And the syntax is almost identical for almost every case. So we're going to do a similar thing. We're reading in our data. But in this case, it's going to be data frame, read under CSV. And again, that file is data.csv. And there is no header. And let's say we want to perform some operation on it. We were looking at like the max above. So we can say I want to create a new object. We'll call you, I don't know, we'll call you callMax for column maximums. And we'll set that equal to data.max. So using the data frame's own method to compute the maximum of each particular column. And then we'll print out column max to see what Dask gives us. And what we see here is like this weird object syntax, saying that there's a thing on disk that has stuff in it. Sorry, a thing in memory that has stuff in it. But it's not the data frame that you were looking for. So what is in there, and this is something that we can inspect, is a dictionary of the tasks that it will be running. So Dask has taken a peek at what's in that location on disk, and what we want to do with it. And it says, this is what I think is the best way to accomplish that task, based on the processors that you have available. And we can see that it's encoding things like the data type that's in here already, the names that we're trying to give the columns. And if I want to know what those column maximums actually are, I'm just going to call a method of that object, and that method is just compute. Oh, of course, yeah. Oh, of course. And again, if there's a part of this where you're like, what? You should say something. Because I can address it now. It will save you from the confusion. So we were talking about getting the results out by calling a method of that object, and that method is called compute. So until now, that call max has just been storing all those tasks that we were trying to perform. And when I run compute, here I get the column maximums for this entire data set. And this should look pretty similar to what we were doing with Pandas above. OK, so we have one more thing to talk about, and that is parallelizing entire jobs. And this one is going to be a little trickier. So we're going to use a library called Celery. Celery is an asynchronous task queue that uses message passing sort of behind the scenes. And what this means is we have to write our own client for how we want to handle these requests. So it's not super, super bad, but it's going to take a little bit of extra typing. And what we're going to do is just create it in a text file. So I'm going to go back here and I want to get a new text file. We'll call you app.py. All right. So what we're going to do in this little task is we have to import Celery and then tell Celery what it is that we want it to do when we give it jobs. So from the library, we're going to import the class of task object, which is called Celery. Our own particular task object, we're just going to call app. And that's going to equal an instance of this class with the name that we give it. We'll just call it jobs, because that's what we're trying to parallelize. And then down here, we will specify that we want our broker to be a particular message passing protocol called QP. It's AMQP. So fun fact, if you write AMPQ, this is a mistake that happens enough to people who write scripts in Celery that there's a specific error message telling you exactly what to change here. Yeah, I'm pretty sure it's AMQP. If not, I guess you'll see the error message, and then we'll have a nice laugh together. All right, so what app is going to give us is a particular kind of decorator syntax for specifying that we want to create jobs that can be run in parallel, that can be run asynchronously. And that particular decorator is called app.task. So we're going to write in that app, the at symbol, app.task. And we'll define a function, and we'll call you, we'll say summarize file. And that'll get a file path. And because we're running a little short on time, we're going to cheat and call in pandas to do the heavy lifting for us to save ourselves some typing. So again, just up there in the import statements, we're going to import pandas as PD. And then down here, we're going to PD read under CSV. That particular file path. And then for the sake of conceptual similarity, we'll just say we want to get those column maxes again. And then we'll write that right back out to disk with 2 CSV. And we'll use the same file name, but we'll prepend like summary to it. So we'll say, use the file name summary under plus the file path that we had before. So we'll save this, and now we can go back to our Jupyter notebook. And in our notebook, we're not actually going to be importing Celery. We're going to be importing that task that we just created. So we're going to say that from that app.py file, we want to import that function name, which was summarize file. And we need to do 2 more things. One of this is to start up our message passing system. So Celery makes preferential use of RabbitMQ. There are other options, but the support is a little weak. And the next thing we need to do is use Celery to start up that app that we've just created. So that A option is for the name of the app, which in this case is just app. And just so we can see what it's sort of doing here, I'm going to specify a log level here that you don't need to worry about as info. And we want to start it up with its workers. And it's not finding my message passer. But to be brief, what you can do with Celery is use the functions the same way that you normally would. So I can do something like call the summary file function on a path like data.csv. And in this particular case, this will just run in plain vanilla Python. And if you're doing this on 1,000 data files, they'll all get run sequentially. If you want to activate that delayed task processing, you're going to access an attribute of this object called delay. And it's into that delay call that you're going to put in the file path that you want. So I will get to work on debugging Rabbit in a minute. But I have about 1 minute left, so I'll say thank you all for listening. Thanks to the DLab for paying me for all these years to have fun with Python. I'd also like to thank Enthought, who in the future will be paying me to have fun with Python. If you have a question for me, I will be outside, or you can reach me later. This is my website, and this is my Twitter handle. And finally, thank you so much for your attention.